Hello everyone. This is the sixth part to be continued. In the last video, I have discussed the application of the Gauss law. Uh, this derived the two derivations, applications of Gauss law. We have seen in my last video that is expression for electric field at any point due to a charged spherical shell and electric field at any point near the surface of the charged conductor. Now we'll see electric flux through the cylinder kept in a uniform electric field, and also these two derivations. This is all about the spherical shell. We have derived a Gauss law, expression of electric field at a point due to the charged spherical conductor. This is the derivation. And also we have seen the electric field at a point near the surface of a charged conductor using a Gauss theorem, that is the surface of any shape. So we have seen the electric field at a point near this surface. This is the derivation of this. So now we are seeing the electric flux to the cylinder kept in a uniform electric field. Let us consider a cylinder which is kept in a uniform electric field. This is the uniform electric field which is directed in this way. This is the uniform electric field. So if you want to find the electric field through this surface, there are three surfaces. Consider this is one surface and this is S1, this is S2, and this is the S3 surfaces, and this is the electric field line. Sorry, these are the electric field lines. So this is the delta S1, this is the S1 surface, and this is the S2 surface, and this is the total curved surface of this cylinder. This is the SA surface. The surface, this is S1 surface, and normal to this. Normal means the perpendicular line which is directed outward from this surface. This is the normal of this surface, and this is direct for this surface. The normal line will be opposite to the electric field lines, and this is the curved surface of the cylinder, which is a normal line will be upward. So now this is a curved surface, and the normal will be always outward and perpendicular to the surface, that is called normal line. So these are the three surfaces. We have to consider the electric field, electric flux to this surface and this surface and this surface. So let us consider say that S1 S2, and the total flux is given. We are finding now electric flux to the cylinder which is kept in a uniform electric field. So total flux is equal to the flux through the surface S1, flux through the surface S1 plus same the flux through the surface S2 plus the flux surface through this surface, that is S3. So we know that the flux formula is, that is the total electric flux is equal to E into S1 cos theta plus E to S2 cos theta 2 cos theta 1. So E3 S3 cos theta 3. So E1 S1 cos theta. So S1 is this surface. The angle between the theta is the angle between the normal of this surface and the electric field line. So both are in the same direction. There is no angle. So theta will be 0. There is no angle. So theta will be 0 here in this case, because no, there is no angle. Theta is 0. So cos 0. You have to take cos 0 plus E2 S2. E2 S2 surface is this surface. So which is in this direction. The normal is in this direction. The angle will be, the electric field line is in this direction. The angle will be 180 degree here. The angle will be 180 degree. So we have to take cos 180 degree. So next comes the E3 S3. This curved surface of the cylinder which is perpendicular to the electric field line. Electric field line is in this direction, and this is the in upward direction. So angle between them is 90 degrees. So you can take cos 90 degree. This is equal to total flux is equal to E1 S1. So cos 0 will be 1, so it will remain E1 S1, cos 0 is 1. So E2 S2. So cos 180 is minus 1. Okay, cos 180 is minus 1. Cos 360 is cos 360 degrees 1. You know that in trigonometric function. So here take minus E2 S2. Cos 180 is minus 1. So minus 1 is multiplied here. So cos 90 will be 0. Sin 90 will be 1. So cos 90 will be 0. So cos 90 degree will be 0. Then this will be the whole equation for the curved surface will be 0. This will be 0. So the electric flux is equal to E1 S1 minus E2 S2. So take common here. We can take electric field lines are all common to all the three surfaces. We can take E1 is equal to E2 because electric field lines will be same in all the three surfaces S1, S2 and S3. So psi is equal to E into S1 minus of S2. So here the surfaces, we have taken a cylinder which having the surfaces, if out this both the surfaces will be equal because the cylinder which having the same here length will be same and different and the distance between these two lengths will be same means the surface area will also be equal. So the S1 is equal to S2, S1 is equal to S2 means S1 minus S2 is equal to always will be equal to 0. So flux is equal to E into 0, E into 0, so then the flux, total flux will be equal to 0. How this S1 is equal to S2 will be 0? How you find out that means if the cylinder if we have taken then the surfaces of that top and bottom spherical surface will be always 0. So we can say that the total electric flux will be 0. Flux cylinder kept in a uniform electric field will be always equal to 0. How we have to show like this? If they ask 2 marks, you can show like this. This is also one of the application of the Gauss law. Here hence we have not used the Gauss law, so I have left this one point to say that electric flux through cylinder kept in a uniform electric field, so that is electric flux will be 0. Next we will go through the two main derivations we have noted before about that these two derivation, that is expression for electric field at a point due to this infinite long straight wire, and expression for electric field due to a uniformly charged infinite plane sheet. Okay, next we'll go to this derivation, and lastly we'll come to this derivation, and these are the last two topics of this chapter. Hence after the completing this chapter I will go to discuss through problems, each and every problem of this chapter, that is electric field and charges. After discussing problems, I'll also discuss some important points which are helpful for the CET questions. I'll discuss only those points, short key points that are helpful for CET questions. After that, I will go to the next chapter, second chapter of the second PUC science. Okay. Now we'll discuss the expression for electric intensity at point due to infinitely long straight wire. Okay, expression for this is derivation by 5 marks. You're going to get in a theory question paper. Expression for an electric field at a point due to an infinity long straight uniformly charged wire. Uniformly means everywhere charge is distributed equally. Uniformly charged wire. They will ask a question, derive an expression for a electric field at a point due to infinitely long straight wire due to uniform charged wire. Let us take a uniform charged wire. This is a wire which is uniformly charged. Uniformly charged long straight. This is a infinity, so I have a dotted line, so I have drawn a dotted line also. We have to find the electric field due to this infinity charged wire. So I have to take a Gaussian surface. This is the application. If you got this question, you have directly and they have asked question, you have to think that this is the application of a Gauss law. So you have to draw a Gaussian surface here and also use the Gauss law, that is psi is equal to q by epsilon naught. So hence consider long straight conducting infinite wire of a if infinite long the long word comes here, long straight wire, then definitely you have to linear, which is equal to linear charge density, that is lambda. This is called linear. If length is given, linear charge density, that is lambda. If surface is given, then sigma. If surface is given, if a long length or something length base they have given, you have to take a lambda, which is linear, and the surface charge density, that is sigma. If they have given a surface, I have discussed this in the last video also, you have to remember these all points. And the last one is a rho if they have given a volume. Okay, let P be a point at a distance r from the conductor. So we have to raise a point let us consider a point P at a distance r from this conductor. Let E be the electric intensity here, E be the electric field at a point P. Let E be a electric field. Consider we have to Gaussian surface in the form of a cylinder. So we have to take that Gaussian surface that must lie where we have to find the electric field. I have already said that Gaussian surface is that imaginary surface. So imaginary surface that must lie on that point where we are finding electric field. So let us draw the Gaussian surface like a cylinder. Only two types of Gaussian surface, that is circle and the cylinder. We have to take these two main Gaussian surfaces are used in each and every derivations or in every problem. This is the Gaussian surfaces. Let us take a Gaussian surface of a cylinder which lies at a point P, which is of length L. This Gaussian surface is length L and P where distance at R. So let us consider Gaussian surface of cylinder. So flux through this circular cross section, we have to find out the flux through these two circular cross sections and also the flux through this curved surface. These are two circular cross sections and due to also this curved surface of that cylinder. So hence we have seen that a flux through the circular cross section cylinder will be always here is a 0, since the area here, see, you know that flux the equation that is equal to number of electric field lines passing through unit area, ds is area into cos theta. So theta is the angle between the normal of that surface to the electric field lines. The electric field is in this direction, that is E is in this direction. Then these surfaces are making this downward surface as a normal downward, and electric field will be in this direction. So angle will be 90 degree. So cos 90 will be always 0. You know that cos 90 degree will be 0. Hence we can easily say that the flux through these two surfaces, how I showed that is due to the flux definition. So the flux through these two cross section will be always 0, always not that is defined due to the electric field lines, that is due to the electric field lines, what is the angle between the normal and the electric field, and here it is 90 degree. Hence the flux through these two cross sections, two circular cross section cylinder is 0. And now we'll say that let the delta S be the, now we have to find out the electric field line due to this curved surface of the cylinder. Only remain this curved surface, this whole total surface, leave these two surfaces, only these two curved surface, this much surface we have to find out the electric field. Okay, let us now consider a small surface area around a P. This is a point P. Let us consider a small surface area. So if we have taken surface area, means we have to use a surface charge density, that is a sigma. I have said that there are three types of surface charge density. Small surface area at the point P of a curved surface of cylinder. Now we have to find out the flux through this delta S, a small surface area. That is let me write the flux. You have to write these all points before going to derivation, then only you get the points. You have to use your NCT questions. They will be given some lines. See those lines, and if you anything point not understood, watch my video once again and you will get how those lines have came, how I explained how these electric field lines, electric field here due to circular cross section 0 I have. So you have to write those all the statements before this, and then directly you go that flux through the small area, small surface area, that is delta S is given by delta psi, that is equal to E into delta S cos theta. So is equal to E into delta S cos what is the angle between here if you taken this small surface area and the normal will be in this direction only, so the angle there is no, the theta will be 0 because theta is the angle between normal of the surface to the electric field line, so theta will be 0, cos 0 will be 1, so the small area's flux will be E into delta S, E into delta S. Over the curved surface area we have got that, and the electric field is same at every point. Electric field will be same at every point. So if we have taken total electric flux, we have taken a small surface area. This is a delta phi is a flux to the small surface area, that is delta S. Now we have to take a total flux. Delta means a small representation of a small. Now the total flux is equal to, will take a phi. Okay, total flux of the curved surface is given by phi equal to summation into summation of delta of psi. So we have this delta phi is a small flux through this small surface area, then the total over the curved surface the electric field is same at every point, so we can take that total electric flux is equal to summation of this delta phi, summation of this small flux through this surfaces. So we can write that psi equal to, I have to just put summation here, summation equal to E into delta S. Then we know that just we have to write E into summation of delta S. Summation of delta is the total surface area of the cylinder. So the area of the cylinder, we know that summation of delta S, area of the cylinder, is how the area of the surface is that 4 pi r square. Here the area of the cylinder is 2 pi rl. This is the area of the cylinder. You have to know that point, which is the area of cylinder. Just put this point here. Then the flux equal to, total flux equal to E into 2 pi RL. This is the flux. Now we have to use the Gauss law, the application of Gauss law here. That is phi is equal to total charge enclosed divided by epsilon naught. Summation, let's just take a summation, total charge enclosed by epsilon naught. So here we are, if here it is a given length, that is a length the conductor, that is L. If here length is given, I have said that I have to take a linear charge density lambda. So if we know that linear charge density is equal to charge per unit length, so you have to take a charge q, that will be q is equal to lambda into L. So phi will be 1 by epsilon naught, that is q is equal to, we know that lambda into L. This is the equation of psi, equation 2, and this is the equation of this. Both let us equate this flux. This is a flux equation 1, and this is the Gauss law. Applying the Gauss law, we have got this equation. So equating these both equation, we will get that E into 2 pi RL equal to 1 by epsilon naught into lambda into L. Then we will get E is equal to this 2 pi will be multiplied down here, that is equal to 1 by 2 pi epsilon naught lambda L divided by RL. L gets cancelled, and equal to 1 by 2 pi epsilon naught into lambda by R. This is the equation of the electric field due to the current carrying long straight uniformly current carrying wire, that is equal to, long means the definitely linear charge density must come, that is E is equal to 1 by 2 pi epsilon naught r lambda. If you have written a lambda r cap, it is in the form of a radially outward unit vector, radially outward with respect to the cylinder. You may also write this equation as E is equal to, just multiply 2 here and 2 here, then we get 4 pi epsilon naught 2 lambda by r, 1 by 4 pi epsilon 2 lambda by. This is also, you can write the equation of the long straight conducting wire. This is of the application of the Gauss law of the fifth derivation. So next we'll go to the infinite plane sheet derivation. Infinite expression for the This is also 5 mass you may get for plane sheet or a plane for a infinite charge conducting long straight conducting wire. 5 mass you can get expression for electric field due to uniformly charged infinite plane sheet. You have to take a plane sheet and you have to derive the electric field due to that plane sheet, charged plane sheet. Let us consider this is a plane sheet which is a charged. Due to this we have to find out the electric field. Consider infinite, this is a plane sheet of a positive charge having a uniform surface density. If they have given a uniformly charged in a plane sheet they have given, so I have to consider a surface charge density. Surface they have given, so I have to consider charge density. Surface, this is sigma is the surface charge density of this plane sheet which is carrying a charge, positive charge. Surface charge density. These all points you have to write before this derivation. You have to write these all points. Consider thin plane sheet which is carrying a surface charge density sigma. Then let E be the electric field at a point P. Let us consider at a point P. Then which is in the direction electric field E. Let us consider a point P which is with the electric field intensity at a point P, and electric one we consider. We have to find out the electric field at a point P, so we have to draw Gaussian surface to find the electric field here. So we must draw Gaussian surface, that is cylinder, or we cannot draw a circle, so which will cannot find out here in this surface or outside surface. The best is a Gaussian surface to draw. Here is a cylinder, so let us draw a cylinder which will pass through this surface. Okay, this is a cylinder which passes through this surface. Let us consider electric field will be in this is also a delta S surface. So we have drawn a Gaussian surface as shown in the diagram. Let delta S be the area of cross section of cylinder on the point P. Here delta S be the, this is the delta S area of the cross section at point P, and here this is also delta S at a point Q. The normal will be of this surface will be in this direction, and the electric field also will be in this direction. So we have to find the electric flux to the curved surface of the cylinder, and these two cross section of the cylinder. Hence the electric flux through the curved surface of this cylinder is 0, because here the area vector are perpendicular here. If you have already discussed this in the last derivation, that is this is a curved surface which is the normal to this surface will be in this direction, so electric field will be in this direction. Then the angle between these two will be 90 degrees. So cos 90 degree, we know that flux is equal to E into ds cos theta. So here theta will be 90 degree to this surface, so the electric flux to this curved surface will be 0. Now we have to find the total flux, that is only the flux through the point P and through the point Q. So let us write, that is you have to write this point also. Why the total flux through the curved surface of a cylinder, curved surface of the cylinder is equal to 0, because theta is equal to 90 degree, that is a normal angle between a normal of a surface between electric field lines is a 90 degrees. So cos 90 degree will be 0, hence the flux will be curved surface through this cylinder will be 0. Next we have only the flux remaining to have to calculate through this surface and this surface. Hence the total electric flux is given by total electric flux is equal to flux through P through P plus flux through Q. So the flux through P plus flux through Q, I have to find out. That is flux is equal to E into delta S cos theta plus E into delta S cos theta. So here we can take that E into delta S is common, and also cos theta is all are same here. Electric field lines is same. Delta S is if you have taken a cylinder which having a length will be same here, so the area of cross section will be both are equal. Area of cross section of these two surfaces will be equal, so all are same. So this both are same, is there will be 2 into E delta S cos theta. I have to see theta here. Theta is the angle between the normal of this surface to the electric field line, that will be 0. Here also will be 180 degree because it is in this direction. Angle electric field line is in this direction, so both are in this direction only. Then the theta will be 0. So cos theta, cos 0 will be 1, cos 0 degree will be 1. So this will remain as 2 into E into delta. Yes, this is a sine. Now we have to apply the cos law. First we have to write the psi equal to E into delta as cos theta formula. Next comes the Gauss law, that is psi is equal to 1 by epsilon naught into summation total charge enclosed, that is equal to U. Here we have to write a charge in terms of a surface charge density, that is which charge density we have to use here. Here it is a given a surface. I have set to say that sigma we have to take down because the surface is given here to surface of the plane sheet. So we know that sigma, that is surface charge density, is equal to charge per unit area, that is Q upon delta. Yes, if you have taken delta small charge, so small area. So then we'll get Q is equal to sigma into delta S, So putting this equation here, we'll get that phi is equal to 1 by epsilon naught sigma into delta S. This is equation 2 and this is equation 1. Now equating these two equations, we will get that 2 into E into delta S, which I have written this here, equal to, we have to write this here, 1 by epsilon naught sigma into delta S. So we have to find out the E here. E equal to delta S cancels. E is equal to sigma upon 2 epsilon naught. This is the electric field due to this plane sheet. The electric field due to this, you have to note down this, then only you will get to this point. Okay, in this case, infinite plane conductor, if the in case of this is sigma upon 2 epsilon naught, in case of an infinite plane conductor of a finite thickness. If they have given, then finite thickness means phi equal to, here flux will be 1 by epsilon naught. Here the sigma into delta S. Here we'll get a 2 sigma into delta S, because charge is enclosed on the both the sheet. If they have given finite thickness, if they have given a finite thickness little bit, this much thickness they have given of something dx or something thickness they have given, then the charge will be enclosed on this surface also and the backside surface also. So we have to, here we have written only Q is equal sigma into delta. Here surface will be doubled, the surface charge density will be doubled if they have given a finite thickness. So I have written 2 sigma into delta S. Then if we equate this and the above 2 into E delta S, we'll get electric field that 2 into delta S equal to 1 by epsilon naught 2 sigma delta S. So all will cancel, we get sigma upon epsilon naught. If we have gotten here 2 get cancel and also delta S, so we'll only get sigma upon epsilon for finite thickness. Then only here only multiplied by 2 if we have infinite. So this is the electric field due to the plane sheet. These are the two main derivations of the application of Gauss law, where we have discussed this one, and also this one long straight wire, where I hope these two derivations have understood to you. If any doubts, please ask me in the comment sections. Thank you. And one more thing, I'll also discuss the problems of all the problems on this chapter. So and also I wanted to start a next chapter. If you have any comments or doubt, if you want to, if you said that you want to start a problems, then I'll definitely going to start a problems. If not, means I am going to start a next chapter, then where I want to discuss the problems after completion of all the chapters. I will discuss, I want to start the problems. So this is the last video of this chapter, and then one more video I want to make, that important points, the key points, and the some important formulas on these chapters that are helpful for a CET. Okay, that is will be last part, that is seventh part, and this is the sixth part continue. So watch these videos, guys. Thank you.